So let's begin here taking a look at our trapezoidal rule. Okay? Now this is something that I want you to really take note of, because up to this point our other approximations for integrals have all used rectangles. Okay? Now, first of all, we're given this basic function, and you can see how drawing a trapezoid will give us an approximate value for what the integral would be. Thanks. Okay? So if I drew this trapezoid, you can see I'm going to get a little bit extra on the top there because this is concave up. But you can see clearly that I'm going to get a better approximation than I would if I did an upper rectangle or if I did a lower rectangle. Okay? So here the trapezoid actually will give me a pretty good approximation. Now, one of the things we got to remember is, how do we find, what's our formula for the area of a trapezoid? Do you remember?
Average of the bases times height.
Okay, good. It's the average of the bases times the height. Okay? And if you know the term from geometry, the average of the bases is the length of the mid-segment. Okay? Maybe you haven't heard that one before. The mid-segment is the segment that connects the midpoints of the two legs. So, there's a new little thing if you didn't learn that in geometry. All right, so in this example here, notice what we end up having. The two bases are going to be f of x sub 0 and f of x sub 1. Okay, those are height. Those are measuring straight up, so they're going to be parallel to each other. So in this case, the area of the trapezoid is going to be f of x sub 0 plus f of x sub 1 over 2. And what is the height of this trapezoid going to be?
X sub 1 minus x sub 0.
Yeah, x sub 1 minus x sub 0. If x sub 0 happened to be 0, then yeah, it would just be x sub 1. But we're going to subtract those, x sub 1 minus x sub 0. So we'll put this over here. X sub 1 minus x sub 0 is our height. Okay, there's our height. It's perpendicular to the two bases. Okay, and here's our base 1 and base 2. Okay? Now, if we actually have this function, this is the function x cubed plus 1, and we're going between x equals 0 and 1, then we can figure, 1 and 2, sorry, we can figure out what that area would be. It would be 2 minus 1 times f of 1 plus f of 2 over 2. Well, f of 1 is going to be 1 cubed plus 1, so that's 2. Okay, 2 minus 1 is 1. So we have 2 plus f of 2 is going to be 8 plus 1, which is 9. Alright, so this whole thing comes out to 11 halves, which is 5 1/2. So that's an approximate value of what the integral would be from 1 to 2 of the x cubed plus 1. Alright, so again, we're doing an approximation. Now, why do we need to learn these approximation methods? Well, because there are a number of functions that simply don't have antiderivatives. Okay? At least not antiderivatives that we're ever going to remember. There are whole books of antiderivatives that people have figured out, but they're not things that we're going to really be able to memorize. All right, so, and some we just don't have ones for yet. So like here, the cube root of x times radical 1 minus x. We don't have an antiderivative of that. So here's what we're going to have. Okay, we have if we need to evaluate a definite integral whose antiderivative cannot be found, the fundamental theorem of calculus cannot be applied because that requires us to know an antiderivative, f of b minus f of a. So we have to use some kind of an approximation technique. This is what your calculator is doing. If you were some kind of a programmer trying to program a calculator to do this, you would have to understand this method, okay, or a similar type of method. So we have here the integral from a to b is going to be approximately b minus a over 2n times f of x sub 0 plus 2 times f of x sub 1 plus 2 times f of x sub 2 plus all the way to 2 times f of x sub n minus 1 plus f of x sub n. Okay? Now, so as n approaches infinity, the value of this whole sum is going to be approaching the value of the integral. Okay, so we have that limit as n approaches infinity thing going again. But where does this come from? I want you guys to really understand where this is coming from before we even do an example. Okay, we already saw that the height of each trapezoid would be whatever b minus a was. Okay, b minus a. Now, where does the 2n come from? Well, the b minus a over n is what we had in the rectangles. That's how we got equal widths, okay? And each of these trapezoids is going to have equal heights in this case. All right, so the height is b minus a over n. Now, let's think about some random function here. And let's say that this is a and this is b. Okay? And actually, let me make this a little bit more drastic so the trapezoids are a little more defined. Okay? So let's say that that b minus a over n takes us to here. Okay? So that's a plus b minus a over n. Okay? Well, let's think about what this trapezoid would be. Okay? The height, or this base of the trapezoid, would be f of a, right? Okay? This base of the trapezoid would be f of a plus b minus a over n. Okay? Which we could call this x sub 0 and this x sub 1. Right? So that's 1, and if I found the area of that trapezoid, it would be 1/2, the average of the bases. So f of a, let's go ahead and use our x sub 0. And this is going to be f of x sub 1, just for simplicity in writing. Okay? So this is going to be f of x sub 0 plus f of x sub 1 over 2, average of the bases, times the height. Okay? Well, the height we already know is b minus a over n. Okay? Well, that's the first rectangle. Let's look at the second rectangle.
What is the n? Like, where does that come from? I know
The n is the same as with rectangles. It's the number of, in this case, trapezoids we're going to use. Okay? Yeah, I should have clarified that. All right, so let's look at a second trapezoid. you'll notice in this trapezoid, okay, instead of keep on writing it this way, it's going to be a plus 2 of the differences. So we'll call this, since this was x sub 1, this is going to be x sub 2. All right? Notice the area for this trapezoid here is going to be b minus a over n times, in this case, f of x sub 1 plus f of x sub 2 all over 2, the average of the bases. Now, I know we've only done 2, but do you see the pattern here?
So it's only 2n because of the 2 on the bottom of the trapezoid.
Okay, we've only done 2 trapezoids, but if I kept going, all of them would have this b minus a over n. So if I'm going to add them up, that's going to be a common factor of all of them, right? Also, all of them have been divided by 2. So I could factor out a half as well. That's where, in the formula, this b minus a over 2n comes from. Okay? If you understand this, it's a whole lot easier to remember. Now, how come we have f of x sub 0 plus 2 of the f of x sub 1s and so on?
Because when you're doing it, like for the first one, you did x sub 0 to x sub 1, and then you used x sub 1 again. So you need to use 2 of them.
Exactly. Think about the bases. The ends you're only going to use as the base of one trapezoid each. So that x sub 0 and x sub n are just going to be used once. But this x sub 1, f of x sub 1 is the base of the first and second trapezoid. F of x sub 2 is the base of the second and third trapezoid. F of x sub 3 would be a base of the third and the fourth trapezoid. So that's why in this formula, the first and the last bases were only used once, but all the ones in the middle are used for 2 trapezoids each. So that's why we have a 2 times that value. Okay? It looks a lot more complicated than it is. Once you understand it, it's a whole lot easier to use. Okay? So let's actually use this with 4 trapezoids, and then again with 8 trapezoids, to approximate the integral from 0 to pi of sine of x dx. Okay? And before we even do that, since this is one that we can do, let's go ahead and find what the answer should be. All right? So what's the integral of sine? Negative cosine. All right? So negative cosine evaluated from 0 to pi, negative 1 minus a negative cosine of 0 is 1. So this should come out to about 2. Okay? Now, which of these is going to give us a value closer to 2? The 8, because we're using more trapezoids. Okay? So watch this. The b minus a over n, okay, b minus a over n is going to be pi minus 0 over 4, or pi over 4. And you can see on the picture over here, it's already drawn with n equal to 4. Okay? So, using our formula, we can say that this is going to be approximately pi over 2 times 4, okay, because it's b minus a over 2n, and then we have to multiply, okay? So what are we going to do? Well, we start with f of a, which is f of 0, plus 2 times f of 1 pi over 4, plus 2 times f of 2 pi over 4, which is pi over 2, plus 2 times f of 3 pi over 4 plus 4 pi over 4 is the end, right? So we're only going to have one of these, f of pi. Okay? Notice we have 4 trapezoids. There end up being 5 things in the parentheses. Okay? Because we are counting both ends. Alright, so now it's really just a matter of figuring out, using our unit circle, sine of 0 is 0. What's sine of pi over 4?
Root 2 over 10.
Root 2 over 2. What's sine of pi over 2? 1. What's sine of 3 pi over 4?
That should be a
Root 2 over 2 again. And what's sine of pi?
0.
0. Okay? So, if I do some reducing here, inside the parentheses, I get, that's canceled, I get a 2 plus 2 root 2, and that's all times pi over 8. Okay? So that gives me a pi over 4 plus pi root 2 over 4. Now, does that give us 2? We could try it. Okay. Pi over 4 comes out pi divided by 4 plus pi times the square root of 2 divided by 4, 1.896. Okay? So that's not a bad approximation. Okay? Not a bad approximation. If we used 8 rectangles on the other hand, let's look at what that would look like first of all. I would have more. So I'd have, if I had 8, I'd have pi over 8, pi over 4. I'd have 3 pi over 8, pi over 2. I'd have 5 pi over 8, 6 pi over 8, 7 pi over 8, and 8 pi over 8. Those would be my different values of x.
So, is there a shortcut, or would you have to do what we just did, but with 8?
You'd have to do that, what we just did with 8, okay? So in this case, with n equals 8, the b minus a over n is going to be pi over 8, like we just saw. Okay? Again, we're doing n equals 8 over here. So the area would be approximately pi over 2 times 8, so pi over 16. And then you would do f of 0 plus 2 times f of pi over 8 plus 2 times f of pi over 4 plus all the way down to plus 2 times f of 7 pi over 8 plus f of pi. Okay? Now, notice here, we would need to use a calculator because the pi over 8s are not on our unit circle. Okay? But we could at least find it. And if this were some function that wasn't just a sine function, then it would be really useful because we'd be able to get a good approximation just by using the calculator, okay? So something would be better than not being able to do it at all, okay? So, yeah.
Is there like a limit version with this that we're gonna learn as well, or no? Like the rectangles?
We can use a limit, do a limit as n approaches infinity, and then it would get us a more accurate one, and that is more like what the calculator would do. You know, it would get increasingly enormous values of n. Okay. I want to show you guys how to do this part. This can be a little tedious, but I want to show you how you can do this on the calculator. If it doesn't make total sense, you can go back and watch the video over until you get it. If it makes absolutely no sense, then just do it the longer way with the calculator. But I want to show you a really useful tool on the calculator called the list. Some of you may have used this before, but I want you to at least get some experience with this. Okay, so one thing that we need to do is, you'll notice we have to do the same thing a bunch of times here, this f of 0, 2f of pi over 8, and so on, okay? One thing that I can do to kind of cut down on how much I'm doing this is actually to use a list. And a list, if you look above the parenthesis, you'll see this little curly bracket, okay? So what I'm going to do is I'm going to hit second and get that curly bracket there. And what I'm going to do first of all is I'm going to put all the different values of x in that I need to do. So 0, and then in a list we separate them by commas. So 0, and then pi over 8. The comma is right next to the left parenthesis. Okay, so pi over 8. Then 2 pi over 8 is pi over 4. And then 3 pi over 8. And then 4 pi over 8, which would be pi over 2. Okay. And then I need 5 pi over 8. And then I need 6 pi over 8, which is 3 pi over 4. 3 pi divided by 4, comma. And then I need 7 pi over 8, so 7 pi divided by 8, comma. And then 8 pi over 8 is pi. Okay? Now I'm going to close the curly bracket right there. Alright, and I'm going to hit enter just in case I mess something up. Alright, but notice it put it as decimals. Alright? Now you might be saying, well, wait a sec, I don't want, I need to take f of each of those. Well, what is f? Sine. Okay? Well, guess what? Making sure I'm in radians, I'm going to hit sine, and I'm going to hit answer. Okay? Now, when you do this with a list, whatever operation you put on the list, it'll do it to each element inside the list. So if I did 5 times that list, it would multiply everything in the list by 5. So check this out. I do that, and there's the sine of pi over 8 is 0.3826, so on. All right? Now, another thing you might be saying is, well, wait a sec, I needed to have 2 of all the ones in the middle. Well, another thing you can do with lists is multiply lists together. So this list has 1, 2, 3, 4, 5, 6, 7, 8, 9 things in it, right? And I need to have 1 of the first and last thing, and I need to have just 2 of everything else. So I'm going to multiply this list by another list. Now, when you multiply a list by a list, it'll multiply the first thing by the first thing, the second thing by the second thing, the third thing by the third thing, and so on. So I want 1 of the first thing, and then 2 of all the rest. So let's see, 1, 2, 3, 4, 5, 6, 7, 8. There should be a total of 9 things, but the last one I only want 1 of. Okay? If you get like an error dimension mismatch, that means you just like miscounted. And one list has more things than the other. Okay? So now when I do that, notice I just multiplied it. 0 times 1 is still 0. If I scroll over here to the end, you'll notice the last one is also 0. I could have just thought about this and said, hey, since the first and last one are 0, it doesn't matter if I multiply them by 1 or 2, and just multiply the whole list by 2. But this is how you could do it with any of them. All right? So that's what I need to total up, right? I need to add those things up. So guess what? Right above stat, you see this list here. So I'm going to hit second list. And if I go over to math, you'll notice number 5 is sum. And I'm going to do the sum of the answer. When you do sum of a list, it'll add up all the things inside of the list. So there we go, it's 10.05. Okay? And then that's what I need to multiply by the pi divided by 16. 1.974. What was this supposed to equal? 2. So that's an even better approximation here. Now, I don't expect you to remember just off of me showing it to you once, all the little steps there. But this is something, if you look at this process and you're like, hey, that's something I could really use, go back and watch this a couple of times and try it. And it will make things a little faster once you get the hang of it. Initially, it won't, okay? Once you get the hang of using your calculator better, it'll make things faster.
Is there a reason it won't scroll to the right? Does it just
it'll only scroll to the right when it's the most recent one.
It didn't do it with that either.
I don't
I don't know.
know. Well, I got an arrow.
You got an error?
Yeah.
Then when you multiplied the lists together?
Yeah.
Probably one of your, like when you did the times 1, 2, 2, 2, 2, 2, you probably either had one too many 2s or you didn't have enough 2s in there. So you don't have the same number of things in the 2 lists. Okay. All right, so that's kind of cool. And we get the approximation then here of 1.974.
So you're okay with us just showing that and then doing it on the calculator, pretty much?
Yeah, if it's a calculator problem. If it's not a calculator problem, we're going to keep them shorter. You know, just like the rectangles. You know, we didn't give you one, hey, do this by hand with 18 rectangles, you know. So, all right. So that's our trapezoid rule. That's the basic principle there. You're just adding up the areas of the different trapezoids. And the formula is kind of a shortcut, so you don't have to do each of them individually. Now, here's a little note. If you compare the trapezoidal rule with the midpoint rule, you'll see that in the trapezoidal rule, you average the function values at the midpoints of the subintervals. But for the midpoint rule, you take the function values of the subinterval midpoints. Okay? So in one case, notice the difference here. It's a fine difference, but you need to pay attention to it. The midpoint rule, you're averaging the x values and plugging that into the function. The trapezoidal rule, you are finding the values of the function at both sides and averaging those. Okay? The difference in these two approximations is going to be very small. All right? But there can be a slight difference. So make sure that you use the appropriate rule, okay? One other comment here I'll make. As you work through the homework, some of the problems say to use Simpson's rule. That's something we're not even covering, so you can forget about those. Notice the directions here. For the first couple, you can check your answer using the fundamental theorem of calculus. For the last three, 11, 17, and 19, you can check your answer just plugging it into your calculator. And of course, it won't be exact, but you can get close. But just pay attention to the directions on there. That's why we printed it out a little differently than just using a screenshot of the book. Okay?